Okay, hello everybody, welcome back once again. We're moving on to chapter 2.5 now, and what we want to talk about is how we can use basically standard deviation to go ahead and make some conclusions or make some general statements about our data. And in particular, we're going to focus on one simple idea about how we can, if we do have the standard deviation and the mean, of course, of a set of data, then we can use that to determine which percentage of our data lies within a certain range. And this range that we'll focus on today will be within a certain number of standard deviations from the mean. So you'll see what I mean in a second, but let's take an example set of data here. And let's use something like student athlete GPAs. So let's suppose that I have a set of student athletes and I have their GPAs, and all of these athletes have a mean GPA of 3.16. And let's suppose that the standard deviation of those GPAs is 0.47. So the question is, what can I go ahead and say? And before we talk about what we can actually say, let's take a look at the histogram here. This is a histogram of, I think this was a histogram from our homework assignment, actually. So there should be, what was it, 87? No, that was the actresses. 75. I think it was 75 student athletes we had in that assignment. And we tabulated all of their GPAs into a histogram, and we found the mean and standard deviation. So let's suppose that that is this data. So here's our data. Our mean is 3.16, which is located right up in the middle here somewhere. It looks like about the center of this data, the balancing point, the clustering point, whatever you want to think about it as. And our standard deviation is 0.47 GPA points. So I have a question for you. If I mark the mean right here in the middle of our data, and I go ahead and I mark the 2 points which are one standard deviation above and below the mean. So what does that mean? It means I take 3.16, our mean, and I subtract our standard deviation of 0.47, and what does that give me? 2.69. And then I go ahead and take the mean, 3.16, and I add 0.47. This gives me the range of GPAs that are within one standard deviation of the mean. 3.16 plus 0.47 is this point here. So let's mark those 2 points. The points one standard deviation above and one standard deviation below our mean. And so my question for you is, which percent of the data, which percent of student GPAs in this particular case, highlighted here in orange, do you think fell within this range? From one standard deviation below, here I've marked it the mean minus the standard deviation, to one standard deviation above. Which percent of the data would you say that that is right there? And so, what did you guess? 60%? 65? 70%? Whatever you guess. Probably a little bit more than 50% if I look at this. I don't think I can quite cover all of these orange sections with the blue sections, so it's probably more than 50%, but about 60% or so seems like a fair guess. And the important thing is to notice that if I did know, for instance, that 60% of my data lied between these two values, it would allow me to start to make conclusions about student GPAs. I could say things like, 60% of student GPAs, it's supposed to be an F, 60% of student GPAs are between 2.69 and 3.63. And notice how nice and easy that is to understand, right? 60% of GPAs are between this value and that value. And similarly, if I went ahead and looked at two standard deviations above and below my mean, if I take 3.16 and I add two 47s, not just one, I'll add 47 twice, I end up down here at 4.10, and 3.16 minus 2 times 47, 0.47 is down here at 2.22. So let's look at how much of my data actually fell within two standard deviations of the mean here. And you can see that almost all of it does. It's not quite 100%. I sort of surpassed my upper limit of GPAs here on the larger side, but on the lesser side I don't quite reach the lower limit of my data. But we're talking about greater than 90% of my data in this particular case being within two standard deviations of the mean. And so the first question we want to talk about is this, and that is there some way that we can say that a certain percent of my data will always lie within, say, 2 or 3 standard deviations of the mean? And the answer is yes. And what we use to come up with percents in this case is called Chebyshev's theorem, and it gives us what we call a lower bound on what percentage of our data must lie within a certain number of standard deviations from the mean. So Chebyshev's theorem says that the portion of data lying within k many standard deviations, where we usually take k to be a number like 2, 3, or 4, within a certain number of standard deviations from the mean is always at least is an important 2 words here, at least 1 minus 1 over k squared. So what does that mean? So for example, what happens when I plug in k equals 2? We just saw a second ago that it seemed like at least 90% of my data was within 2 standard deviations of the mean in this particular example. And if I use Chebyshev's theorem and I plug in k equals 2, then this tells me that the portion of data lying within 2 standard deviations of the mean is at least 1 minus 1 over 2 squared percent. 1 minus 1 over 2 squared is, of course, just 1 minus 1 over 4, and 1 minus 1 over 4 is 3 over 4. So what this theorem tells us is that for any set of data, I always have at least 75% of the data points within 2 standard deviations of the mean. Can it be more than 75%? You bet it can. We just saw an example where it looked like it was a lot more than 75%. But not all data sets are sort of grouped around the mean as nicely as this set was. And what we'll see soon is that if our data does happen to have a nice sort of grouping property around the mean like this one does, then I can actually do much better than Chebyshev's theorem. But Chebyshev's theorem is a powerful result because it works for absolutely any data set whatsoever. We don't need to know anything about the distribution or how the points are spread out. I can always say that I have, say, 75% of my data within 2 standard deviations of the mean, and I can go ahead and extend this to other percents too. If I plug in 3, 4, or 5, for example, Chebyshev will tell me that there's always 89% of my data within 3 standard deviations of the mean, 94% of my data within 4 standard deviations, and so on, and so on, and so on. So notice that if I plug in k equals 1 to Chebyshev's theorem, for instance, then what I can conclude is that for absolutely any set of data, at least 1 minus 1 over 1 squared, but that's just 0, at least 0% of the data lies within 1 standard deviation from the mean. So what that means is without any additional assumptions, I can't make any conclusions about how much of my data lies between 1 standard deviation below and 1 standard deviation above. But of course, in particular with our example, and as we'll see, as with any example of data, where that data tends to cluster around the mean, you're going to get a fairly significant chunk of your data within that range of 1 standard deviation below and 1 standard deviation above. But Chebyshev is sort of no help to us in this case. So what we can do is we can actually do a lot better using a different rule other than Chebyshev's theorem, but we need to make an assumption about the way that our data is distributed. And that assumption is basically that our data is symmetrical around the mean. And so what that means is if I take my data and I look where the average is, or the mean is, if our data has the property that our mean is in the center of our data, that these highest sort of occurring frequencies tend to happen right up around that mean, and as we move away from the mean, above and below, our data tends to decrease in frequency in a sort of symmetrical way. And what happens when all of these things occur is that our data ends up resembling, if I sort of take my pen and I draw a sort of smooth function to cover these frequencies, to approximate these frequencies, it ends up looking a little bit like a bell. And so we call data with these properties bell-shaped. Or if we want to be fancier and use more technical words, we call them normal distributions or Gaussian distributions, in honor of Carl Friedrich Gauss, the mathematician, who studied these curves in detail. So if my data has these properties, basically you can think if it looks like a bell curve, if it looks bell-shaped when I look at its distribution, then we can do a lot better than Chebyshev's theorem. And this is a very famous type of distribution. There are countless examples in nature and in the real world where we see this distribution, so it's very popular, and it's not a big stretch to think that a lot of our data, in particular the data we see in this curve, will end up having this sort of shape. So it's a very important shape to understand, and things like IQ scores, grades on tests, any measurements of size, heights, weights, all of these things tend to have this bell-shaped distribution. And if our data is indeed bell-curved, then the analogous result to sort of Chebyshev's result, which is a much more powerful result, is called the empirical rule, or the 68, 95, 99.7 rule. And what this says is basically the real rule is just this little image right here, but it says within one standard deviation below and above the mean. So if I have my mean centered right here into my data, if this is GPA scores, this would be 3.16 in our last example, and so on and so on. And if I take the range from one standard deviation below to one standard deviation above, I'll always find 68% of my data in that range. And so it actually tells us a little bit more. It's not just 68% from this entire range, one standard deviation below to above. I can actually say that exactly 34% of my data should be between the mean and one standard deviation above, and 34% of my data should be between the mean and one standard deviation below. So this tells me a little bit more. For instance, if I look back at our data here, if this data was a perfect bell curve, if it was perfectly normally distributed, then I would be able to say that 34% of my GPA scores should be between 2.69 and 3.16. And I could also say that 68% of my GPA scores should be between this entire range, from 2.69 to 3.63. And I can use this result not just for one standard deviation, but 2 or 3 standard deviations as well. In a perfect bell curve, I'll have 95% of my data from 2 standard deviations below to 2 standard deviations above. In our example, that would mean that we should have, if I trace my way all the way back here, we should have about 95% of our data, if this was indeed a perfect bell curve, what it's not, but if it's approximately bell-shaped, we can still use this as an approximation. So what I could say is that if this data is approximately bell-shaped, I can assume that this range here constitutes about 95% of my data, which actually looks to be a pretty fair estimate in this case here. So this rule here, the empirical rule, the 68, 95, 99.7 rule, like I said, it doesn't just apply to only these 3 numbers, 68, 95, and 99.7. These are the percents of data when I am normally distributed that lie between 1 standard deviation, 2 standard deviation, and 3 standard deviations of the mean. But don't forget that I can also use this to determine the percent of my data from 1 standard deviation below to, say, 2 standard deviations above, right? It tells me that this portion of my data should be about, well, 34 plus 34 plus 13.5, that's 81.5. So that should be 81.5% of my data, and so on and so on. So I can use this graph down here to actually go ahead and figure out what percentage of my data, when that data is normally distributed, lies between any of these different values, from 3 standard deviations below to 3 standard deviations above. I can find out what percentage of my data is between here and here. I can find out what percentage of my data is from here to here, and so on, and so on, and so on. All I have to do is look at this and take the sum of these percents, and that should tell me exactly how much is there. That's it for now. We'll do some examples in a minute.